In this tutorial, you will learn how to create custom controls in wxWidgets. We will build a fully functional custom chart control from scratch, complete with dynamic margins and auto-resizing. Our control will also be able to handle all sorts of data ranges gracefully by automatically generating the horizontal axis labels. You will also learn how to implement interactions with the user, how to handle mouse events, and use Affine Transformations to move and rotate objects on the canvas. We will also talk about creating custom events and providing two-way communication between your custom control and the rest of the application. Let's start with something simple though, a single rectangle. We'll need an empty wxWidgets app. You can download the first commit of the Git repository to start. The address is in the description of this video, or you can watch my wxWidgets and CMake setup video if you want to learn more on how this setup works. Alright, the first thing we need is a class for our custom control. We need to inherit from at least the wxWindow class, but we can use any other subclass that derives from wxWindow, like wxPanel for example. Here we declare a pretty standard constructor with basic parameters like ID or a position. All these will be passed to the base class constructor. To do custom painting, we need the handler for the paint event, where all the custom drawing will take place. We start our implementation file, which includes, for headers, needed to access the graphic context and graphic primitives. Then we proceed with the constructor implementation. Note the background style, indicating that we will paint the control ourselves. We also need to make sure our onPaint handler is actually connected to the paint event. In the handler's body, we need the pointer to the graphics context. First, we acquire the device context, or DC. We use the auto-buffered context to avoid flickering problems in Windows. The clear method is also needed for Windows. Without it, we would end up with some drawing artifacts left on the screen. We set the size and the origin of our rectangle using the fromDIP method. The DIP means density-independent pixels, and this method ensures our sizes are scaled correctly for high-density displays like 4K on Windows. Mac OS does this scaling automatically, but since we want our application to run correctly on all platforms and resolutions, we need to use fromDIP every time we are dealing with absolute pixel values. Note also that in wxWidgets, the coordinate system starts at the 00 point in the top left corner of your control area. In our case, the control will fill the window, so the control area is the full window area, excluding the title bar and the status bar. The first pixel value, the x coordinate, describes the distance of the upper left corner of the rectangle from the left side of the control area. The y coordinate is the distance of the top of the rectangle from the top of the control area. The last thing is setting the fill color, which is done by setting the correct brush. We use a predefined red brush and draw the rectangle on the screen. After that, the graphics context is deleted. After adding our source file to the CMake configuration, we head to our mainframe, where we'll be using our new control. Just as with any built-in control, we declare the class member variable and we instantiate it in the constructor, adding it to our sizer. If you don't know how sizers work, I recommend my wxWidgets video on using sizers and splitters to create a basic layout for an application. Alright, we have a rectangle. Let's now add a text in the center. We need to set the font and simply draw the text at the correct location. The text does not look centered though, and that's because what we specified in the drawText method are the coordinates of the top left corner of the text. So in order to center it, we need to move the origin of the text by the half of the text width to the left and half of the text height up. But what is the height and width of the text? wxWidgets has a function for measuring that. We first need to set the font, prepare output variables, and then call the getTextExtend method. Our output variables will contain the text dimensions, and we can use them to shift the text placement so that it's centered in the rectangle. Let's now try some transformations on our rectangle. We will see how to rotate our object, move it to a different position, and change its size. We will do that by using geometric transformations called affine transforms. Suppose we have a set of lines that form a particular shape. We would like to rotate this object around the top left corner of the screen. To do this, we could calculate the position of one of our shape's corners after rotation, and then repeat that for the rest of the points. How to calculate the position of a point after rotation though? Well, we could use our sophisticated high school trigonometry skills to come up with the formula and then implement that formula in our code. But nobody really does that, because in computer graphics there is a standard way of doing it, through affine transforms. Suppose we have a point in 2D space with the coordinates x1, y1, and we want to transform it according to some rule. In the previous example, the rule was to rotate the point clockwise by some predetermined angle around the top left corner of the screen. But in general, the formula for transforming a point would be... It turns out that for transformations like rotation and scaling, the function t can be expressed as a matrix multiplication, and that function is called linear mapping. Now, if you don't know anything about matrices or linear algebra, this may sound scary, but I'll do my best to explain it as simply as possible. Most of the time you won't be typing actual matrix values in your code, but rather calling predefined methods like rotate or translate. Still, the very basic knowledge of underlying math is necessary for proper intuition about composing affine transformations and reverting them to switch back and forth between different coordinate systems. Let's say we want to scale our object by 2, that is double its size. To do that, we need to multiply the coordinate of each point by 2. So if the original point was x1, y1, and the resulting point is x2, y2, the formula for calculating the resulting point coordinates is... Using vectors and matrices, we can write this in a single equation. The columns x2, y2 and x1, y1 are called vectors, and M is a matrix. In case of translation by 2, our matrix looks like this. And the whole equation expands to... How do we multiply a matrix by a vector? We multiply the numbers in matrix rows by the numbers in vectors column and add them together. A nice visual trick when you are new to matrix multiplication is to move the vector above the matrix and write the result below, doing multiplication step by step like this. We multiply the first number in the first row by the first number in the vector, and add the second number in that row multiplied by the second number in the vector. We repeat that for the second row of the matrix. Now we can get rid of the zeros and see that the resulting vector is indeed just the first one scaled by 2. There is also a linear transformation for rotation. If we apply this matrix to our point x1, y1, and do the multiplication, again multiplying the numbers from left to right and from top to bottom, we will see that we come up with the same result as with our high school trigonometric equations. By using a 2 by 2 matrix, we cannot achieve translation, that is, move the point by a constant number, for example 50 pixels to the right. We need to extend our linear transformation matrix to accommodate translation. Linear transformation combined with translation is called affine transformation. Translation, in practice, is nothing more than moving a point by some value along the x-axis and some possibly different value along the y-axis. That's just adding a number to your x1 and y1 values. And you cannot do this using the 2 by 2 matrix. We will need to extend the matrix to 3 by 3 and add another row to our vectors like this. If you multiply this matrix by our x1, y1 vector, you will get the x1 plus tx, y1 plus ty, as expected. Our scaling matrix becomes where Sx is the scaling factor along x-axis and Sy is the scaling factor along y-axis. And the rotation matrix. Notice that the 2 by 2 corner of our affine transformation matrix is exactly the same as our 2 by 2 linear transformation matrix. In general, for a 3 by 3 affine transformation matrix of this kind, this part is the linear transformation part, and this one is a translation vector. This becomes relevant when we consider composition of affine transformations. It turns out we can combine translations, rotations, and scaling by multiplying the matrices. For example, we can combine rotation with translation by chaining the multiplications like this. Now we need to be careful there, as the matrix multiplication is not commutative. This means that A times B is not necessarily the same as B times A. In other words, the order of operations matter. If we multiply these two matrices, we get the following result. If we change the order, the result is different. Let's take a closer look. I mentioned that the 2 by 2 part of the affine transformation matrix is responsible for the linear transformation, and the 2 by 1 column on the right is responsible for translation. How that column looks in our combined matrix? Well, in the first case it's just tx, ty, but in the second case it's more complex. It looks familiar though, take a look. So it looks like the rotation, or the linear part of the first transform, affects the translation vector from the second transform. What exactly is going on here? Let R be our rotation matrix and T our translation matrix. We combine these two to transform a point P and obtain a new point Q. We cannot change the order of the matrices, as matrix multiplication is, in general, not commutative. But it is associative, so we can change grouping or the order of the calculations. We can first calculate the R times T and then multiply that by P. Or calculate T times P and then multiply that by R on the left. We can interpret that as transforming P by T, because that's what T times P means, to obtain P prime, and then transforming P prime by R to get Q. We move from the right, or from P, to the result Q on the left. In other words, the transform on the left is applied to everything on the right. Not only the point P is rotated, but the transform T as well. This is reflected in the matrix R times T. We already shown it looks like this. If we name the 2 by 2 linear part of the first matrix capital A and the translation part of the second matrix a lowercase b, we can see that the resulting translation vector is A times B. Actually, in general, we need to add the translation of the first matrix. In a rotation transform, it's 0. The linear part of the result is also a combination of the two matrices. It is a result of multiplication of their linear parts. It is clear now that the matrix on the left transforms the matrix on the right. We'll see in a moment how the order of the transformations affects the behavior of the objects on canvas. But we need to understand two more concepts before that. The first one is converting between coordinate systems. Let's draw a rectangle centered at 0, 0. Suppose the rectangle crosses the horizontal axis at x and the vertical axis at y. That means the bottom right corner of the rectangle is at xy. Now we translate and rotate our rectangle, and here is its new position on the screen. We can visualize that as a transformation of the actual coordinate system. If we think about it, the bottom right corner of the rectangle in our new coordinate system, it's still at xy from the perspective of this rotated and translated axis. From the perspective of the old system, however, the coordinates of that point are different. Let's call them xm and ym. Let's use the letter m for the matrix we use to transform our rectangle. So the point after translation, xm, ym, is equal to the original point multiplied by that matrix. The question is, can we do the opposite? Suppose we know the xm and ym values, and we need an answer to a question. Given xm, ym, and the matrix M, what was the original point xy, which after being transformed by m, gave us a point xm, ym? Can we just divide the transformation equation by m to get an answer? Well, kind of. We can multiply both sides by the inverse of m. A matrix multiplied by its inverse on the left results in an identity matrix. And multiplying a vector by an identity matrix is like multiplying by 1. So we can erase that. On the other side, we are left with the inverse matrix, and we now have a way to convert back and forth between transformed coordinate system for any point. This is very useful for various calculations for determining the relationships between objects in different coordinate systems. Note that, in general, not every matrix can be inverted. The affine transformation matrix is a special case, and every affine transformation matrix is invertible. So, as long as you build your matrices by combining scaling, translations and rotations, as opposed to manually changing the numerical values inside the matrix, you will be safe. Inverting a matrix is a pretty complicated numerical operation. That's why you will usually call a framework method to do that for you. It can be useful, however, to understand the construction of the inverse affine transform in terms of the linear part and the translation part of the matrix. If our transform has the linear part m and the translation part b, then inverse of that transform can be expressed as shown on the right. So the linear part is inverted, and the translation part is negated and transformed by the inverse of the linear part. One last remark before we continue with our application. If you look at the wx affine transform sources, you will see that the calculations look reverted. The vectors are horizontal instead of vertical, like in our examples. The matrices have columns and rows mixed up, and the order of the operations is reversed. This is actually okay and mathematically equivalent to the equations presented in this tutorial. Consider a matrix. A matrix transposition is an operation that converts every row to a column by flipping the matrix in a particular way. For a vector, the transposition turns a column vector into a row vector. For matrices that can be multiplied, this relationship holds. This also works for multiplying vectors and matrices. Or equivalent, the part on the left is the wxWidgets way, resulting in a row vector transposed to a column vector. that column vector equals to the right side, which is the classic way described in this tutorial. So both our way of calculating transformations and wxWidgets way are equivalent. Let's go back to our tutorial application and implement some basic transforms. Here in our drawing canvas CPP file, we change the position of the rectangle so it's centered at 0, 0. Next step is to create a matrix. By default, the matrix is constructed as an identity matrix, with ones along the diagonal and zeros everywhere else. Think of it as a neutral matrix. So we can immediately add the transformations. The translate, rotate and scale methods change the object in place, so our transform variable contains a transformation which is a composition of these three operations. How exactly are they composed? Calling a method like translate or rotate builds a requested matrix and then multiplies it on the right side of its object. At creation, the variable transform contains an identity matrix. By calling translate, we multiply it by a translation matrix, and then by rotation and scale matrices. Remember, do not be confused by wxWidgets method descriptions, which use transpose notation. Multiplying transposed matrices on the left is the same as multiplying non-transposed on the right. In this tutorial, we use classic mathematical notation for consistency. So each new matrix is added at the end of the computation chain. This means the last matrix is the first to be applied to a transformed point or object, as discussed before. The object will first be scaled, then rotated around 0, 0, and finally translated. Note the argument to the rotate method. The angle is specified in radians. Pi radians represent the straight angle, so pi divided by 3 radians equals 60 degrees. We can use the transform variable in various ways. One of the most useful is to change the graphic context transform using the setTransform method. After that call, everything we draw on that context will be transformed using our matrix, until we call setTransform with another matrix. Note that the text itself is also rotated. That's something we wouldn't be able to do manually by calculating pixel positions. Let's examine how we got to that transformed rectangle. Let's make things a little bit more interesting by including asymmetric scaling. We will scale our rectangle by a scale of 3 horizontally and by 2 vertically. We started with a rectangle centered at 0, 0 in the top left corner of our canvas. Reading the transforms from the last one, we applied scaling, rotation, and translation. But what if we change the order a bit? This looks weird. We transformed the rectangle using rotation and then we applied scaling to that rotated object. Since the scaling is larger on the horizontal axis, the rotated object is stretched horizontally. The third combination should be easy now. We rotate, translate and scale, meaning our translation vector is also scaled. That's why the whole thing moved more to the right and down. How about this one? Here's the result. The rectangle is gone. What happened? Well, we translated the object and then applied rotation to the whole thing. Remember that we rotate around 0, 0. Because of the translation, the rotation radius got bigger and the rectangle disappeared on the screen. By decreasing the angle of the rotation, we can see that effect. Alright, that should do for a basic affine transforms explanation. Let's move on to our application. Since we would like to show as many rectangles as we want, it's a good idea to create a class representing the objects being displayed. Here we create a graphic object class just for that purpose. It's a simple data type with all the variables public. We need a rectangle representing the initial position and dimensions of the object, a color, a text to be displayed, and a matrix representing current transformation of that object. In our drawing canvas C++ file, we create addRect method where the user of our class can specify the parameters of the object to be added to the canvas. We'll also need a list of our objects. We will be doing a lot of adding, removing and replacing, for example bringing the clicked rectangle to the front, so a list seems to be a better container for that purpose than a vector. The implementation of the addRect method is pretty straightforward. We create a rectangle centered at 0, 0. That's why we shift the origin of the rectangle by half of the width to the left and half of the height up. We then create the transform, applying rotation and translation, to match the parameters provided to the function. The onPaint method must be altered so that it iterates over all the rectangles in our list. The body of the method does not change much, except we obviously need to use the values for position, transform, title, and color from the object on the list. Note that after every iteration of the loop, the next rectangle is drawn over already drawn ones. That means our list represents a stack of rectangles, with the last element being on the top, meaning closest to the user in terms of the Z order. The next step is to add some sample rectangles. For now, we'll hard-code 3 rectangles, and we'll add an ability for the user to add or remove rectangles later. We'll add a red, blue, and a semi-transparent rectangle, so that we can see how these are stacked together. In order to enable user interaction, we need basic handlers for mouse events. Click event, handled by onMouseDown method, move event, onMouseUp to handle end of dragging when user releases the mouse button, and onMouseLeave, which indicates the cursor leaving the control area. We also add helper finish drag and finish rotation methods, along with a pointer to the object being dragged, and a flag determining if the user initiated translation or rotation event. The last member variable is needed to correctly determine the dragging vector and will be explained in a second. Going back to our implementation file, we first bind the event handler methods to the corresponding mouse events. In the onMouseDown method, we will see how to use inverted affine matrix to determine relationship between a transformed object and a point. In particular, we will use it to check if the point lies inside the rectangle. The idea is to check all the rectangles starting from the top until we find the rectangle which contains the click point. Since the rectangles are stacked one on top of another, with the topmost rectangle being at the end of the list, this ensures we will get the first clicked rectangle from the user's point of view and not some other rectangle below. To do this, we are searching the list using reverse iterators, effectively starting from the end, or in other words, the top of the stack. the click pose variable holds the click position in the control's coordinates. We then use the inverted transform of a given rectangle to convert that position to the rectangle's coordinates. Then it's just a matter of calling the contains method of the rectangle to check if the converted point lies inside. Again, here is how this works. The click pose variable contains the click position from the perspective of the main coordinate system. When using inverse transform from the object, we get the dx, dy coordinates from the perspective of that object. Now we need to check if these coordinates are within the bounds of the rectangle, either by using formulas directly or by calling the contains method, which does similar calculation. We check the result of our search. If the iterator contains anything other than rand, it means the user clicked on the rectangle and we are ready to start the drag or rotation process. The first step is to bring the clicked rectangle to the top of the stack, as it would look very weird if the user were able to drag a rectangle underneath other rectangles. This, unfortunately, requires some iterator tricks. We need to convert the backward iterator to a forward iterator. Remember, we searched the list from the end using the reverse iterators, because the erase method accepts only forward iterators. After that, the clicked rectangle is copied to the back of the list, that is to the top of the stack, using pushback, and the original is erased to complete the move. We set the dragged object pointer to the last object in the list. We need to use priv, because the end iterator points to a special element behind the last one. The click point is stored in last drag origin, which will be used in the mouse move handlers to calculate drag or rotation amount. Finally, the rotation flag is set to true if the user holds the Alt key or the Option key on Mac when clicking the rectangle. In onMouseMove, we check if the user initiated the dragging action and what's their intention, to rotate or to move the rectangle. The rotation case is actually simpler. We want to rotate counterclockwise when the user drags the mouse up and clockwise when they drag down. So we calculated the vertical difference between last seen mouse position and the current one. Then we rotate the rectangle by that amount divided by some arbitrary factor to reduce the rotation speed. If the user wants to move the rectangle, we first need to calculate the direction and magnitude of the move. The drag vector is technically a wx point to d, but its mx and my fields should be interpreted not as some point in space, but rather as the amount of movement along the vertical and horizontal axes since the last registered mouse pointer location. How can we apply this displacement to our rectangle? We could try to simply call transform translate with the parameters drag vector mx and drag vector my, but as we have shown before, this would lead to our translation being transformed by the linear transformation component of the matrix. For example, if the user intended to move an already rotated rectangle down in a straight line, the drag direction would get rotated and the whole rectangle would move along a slanted line. We need to counteract this possible rotation to bring back the vector to the desired orientation. To do this, we take the full inverse of the current transform. This creates a transform that reverses both the linear part and the translation part. By using transform distance, we apply only the linear part to our drag vector, and then we translate the object by that altered vector. Since we are using differences between points, or distances, and not points, we cannot apply the full inverse, because that would bring us back to the center of the coordinate system. Intuitively, when transforming distances, use transform distance method. When transforming points, use transform point. At the end of the onMouseMove method, we update the drag origin to the current mouse pointer position and trigger repaint of the control by calling refresh. That's in essence all of our drag and rotation code. We just need to handle the end of the drag process by implementing methods which trigger when the user releases the mouse button or leaves the control area. Let's see how it works. The selected rectangle is always brought to front, and then if the user proceeds to drag the object while holding the left mouse button, the rectangle moves on the screen. If the user holds the Alt key when dragging, the object rotates around its center. All of that is accomplished by using the Affine Transformations. Let's implement more user interactions. We'll add buttons allowing the user to add a random rectangle or remove the top one. When the rectangle is added or removed from the canvas, the control will also send custom events which will be processed in the main frame. Thanks to these two mechanisms, we will establish a two-way communication between our custom control and the rest of the application. For starters, we declare two custom events, one for communicating to the rest of the application that a rectangle has been added, and the other for notifying about the rectangle removal. Both events are of built-in type wxCommand event. You could always use a custom class for your events, but most of the time this is unnecessary, as built-in events are able to transport payload, meaning you can send custom data with your event. In our example, we will send a string identifying the rectangle which has been added or removed. So in the header file, we use event declaration macros. Event definitions will be added in the implementation file. Staying in the header, we add the remove top rect method to complement the add rect which is already there. This is the public interface for the other application components to use to manipulate our canvas. We also add a method to get the current object count, along with some helper functions for the opposite communication direction, sending events from our canvas to other objects in the application. In the implementation file, we have to add definition macros for our events, and we can proceed with implementing the actual communication. First, in the addRect method, we simply call the helper function sendRectAddedEvent with our rectangle name as a payload text to be transmitted by the event. Next, we implement the removeTopRect method by essentially removing the top element unless the object list is empty or we are in the middle of the user-initiated dragging process. We then call sendRectRemovedEvent with the removed rectangle's name. Finally, the methods that do the actual sending of the events. We create an event, passing our custom type as the first parameter, and then use setEventObject to set the originating object to our canvas control. The payload is set using setString, and the event is sent using processWindowEvent method. The sendRectRemovedEvent implementation is nearly identical, except of course for the event type. Now we need to connect the controls in our main frame to the canvas. We'll need random number generators to create rectangles, hence the include directive. The handlers for add/remove buttons will be responsible for calling the addRect and the removeTopRect methods from the canvas class, while onRectAdded and onRectRemoved will react to events sent by the canvas and update the status bar with relevant information. We also add a helper createButtonPanel method, a rectangle count, and a Mersenne twister random number generator. In the myFrame constructor, the most important additions are the bind calls. As you can see, there is no difference between connecting custom events and built-in ones. We also update our sizer with the new button panel and create a status bar with the initial text. The onAdd button click needs to generate a random rectangle. We set up a bunch of random distributions with ranges for rectangle size, its position along the x and y axis, angle, and color. After that, we call the addRect method, passing the random numbers for the parameters, along with the rectangle name string indicating its number. The remove button click handler is much simpler, with just a call to remove the topmost rectangle. The handlers for the canvas events are also straightforward. We simply update the status bar with a string containing the rectangle name passed in the event's payload. Finally, the helper method for arranging the buttons. This is very basic stuff, just adding two buttons with a sizer and event handlers to add or remove rectangles from the canvas. Let's check out how our two-way communication between the canvas and the rest of the app works. We can move and rotate the rectangles as before, and we are also able to add new ones. That's the communication from the main window to the control. Note also the status bar change. This is the communication in the opposite way, from the canvas to the main window. The same goes for removing rectangles. Note that we always remove the rectangle on the top, possibly brought to front by the user, and not necessarily the last one added. Let's now create something that's actually useful, a chart control. As always, we need a class declaration, deriving from wxWindow, and a basic constructor. For the sake of simplicity, we declare both our vector of values to be displayed and the chart title as public members. In the implementation file, we add basic includes and proceed with implementing the constructor. Note the full repaint on resize parameter in the base constructor. Our control has to be repainted if size changes, because our chart will be stretched dynamically. This is the default behavior on Mac and Linux, but we need to specify this parameter for Windows. Our onPaint method is very simple for now, just doing some basic context setup. We will add a drawing later. We also add the CPP file to CMake, and we show the chart control object in the main file, adding it to the box sizer as usual. At this point, we only have an empty control, so let's add some content. We start with the title of the chart. We need a little larger font than the default one, but we keep other parameters of the font unchanged. Our control needs to look good, regardless if someone uses the default light Windows theme or maybe a dark theme on Mac OS. To achieve this, we use System Settings getAppearance method to determine the color of the text. Before we start drawing anything, we need to calculate margins and areas to be used for drawing. The left and right margins, represented by the margin x variable, equal to 1/8 of the control width. We do similar calculation for the top margin, making sure we have enough space for the title text and the space around it. There will be nothing on the bottom of the chart, so we set the bottom margin to 1/8 of the control height. Here is a visualization of these margins. Because these values are defined in relation to the control dimensions and title size, the margins will change dynamically as the user resizes the window. Calling inset on a rectangle reduces its size from the left, top, right and bottom sides, and we end up with the chart area variable representing just the area where chart content will be drawn. We proceed to draw the title text, centering it in a similar fashion as we did with the text inside rectangles. Horizontally, the text is centered in the middle of the control, while vertically it's positioned in the middle of previously calculated top margin. For now, we simply draw a red rectangle in the chart area to see how this part reacts to changes in the window size. We set the chart title and run the program. The elements of the chart do stretch and move correctly, keeping their alignment as the window size changes. Let's draw the horizontal grid lines. For drawing the lines, calculating chart values corresponding to these lines, and calculating the positions of actual data points in the chart, we will use Affine Transformations in an interesting way. We start with a transformation that maps values between 0 and 1 to pixel positions on the chart area. Imagine an abstract representation of our chart area stretching from 0, 0 to 1, 1. The point 0, 0 represents the top left corner of our area, point 1, 1 the bottom right corner, and values in between are scaled in a linear fashion. Our transform converting this normalized representation to the chart area pixels consists of translation by the chart area origin, so that the 0, 0 point maps to the upper left corner, and asymmetric scaling by the chart area's width and height. This allows us to avoid using chart area width and height in every calculation. We simplify the math by using abstract 0,1 box and then use Affine Transform to make the final conversion to the chart area. After preparing the transform, we set the line count and choose the gray color. We loop through the lines and set the normalized y coordinate for each line. We want our lines to span the whole normalized range, including both 0 and 1, so that the first line will mark the top of the chart area and the last line will end up at the bottom. To achieve that, we need to divide the index by the lines count -1, which is the maximum value of the loop index. We then use our transform to convert the normalized coordinates to the chart area. Note that for the x-coordinate, we use 0 for the left point of each line and 1 for the right point. This ensures that the lines will span the whole chart area from left to right. We create an array of these points and draw a line between them using the stroke lines method. The first argument is the point count, and the second is the array of points to be connected. We use 2 points because we draw only a single line with each loop iteration. Next, we get rid of the red rectangle and finish our grid by drawing the lines on the left and on the right. Again, we specify the positions of line endpoints using normalized coordinates, and we are letting the transform matrix do the final conversion to the actual pixels. The grid is complete and it works great, correctly stretching as the window is being resized. It does need some labels so that the user knows what values the grid lines represent. We will start with a simple assumption that the lowest line on the chart marks the lowest value we want to plot, and the highest value always sits on the top line. This will lead to some weird numbers, but we will fix that problem at the end of the tutorial. The labels to chart area margin ensures that the grid labels on the left do not touch the chart area. We set that to a small value of 10 pixels. We need to find the minimum and maximum element of the values vector. We use standard C++ methods to do that. These methods return an iterator, so we dereference it using the star operator. Here's another transform matrix. This time we want to map the 0 to 1 range to the corresponding values. Note that, just as with the previous matrix, value of 0 represents the top of the chart, that is the highest value, and 1 represents the bottom, or the lowest value. Achieving this kind of reversed mapping is a bit complicated, so let's examine how it is done. We will focus on the vertical values, as these will be used to calculate labels. Let's see what happens to our input value y. We first scale it by our value span, then flip it by -1, reversing the mapping, and finally we add the high value. As a result, 0 turns to high value, because 0 means top of the chart, 1 is mapped to low value, and for example 0.5 is exactly in the middle. We set the font to our labels, and then jump right into the loop used to draw horizontal lines. Thanks to the transform, calculating the value for each line is as simple as calling transform point with our normalized horizontal line coordinate. We set the x to 0, as we won't be using it here. Only the y value is interesting to us at this point. Now it's just a matter of formatting the text representing the value at a line and truncating it if it gets too wide. We use the ellipsize method to fill the middle of the text with dots if it's larger than our left margin. If that happens, the user will have to resize the window to increase the margins and make sure the value fits. Next, we use familiar text measurement method so that we are able to center the text vertically in the middle of each grid line and align it to the right next to the corresponding line. Finally, we go back to the main frame and add the actual values to be plotted on the chart. We don't have the plot code yet, but after running the program we can see the labels are correctly displayed. The line at the bottom corresponds to the lowest value in our vector, and the line on the top marks the highest one. The labels also move with the lines, as the chart area changes its size. Plotting the actual values is actually pretty simple, since we have all the components in place. We just need the last one step involving our transform matrices. We already have two transforms, one for converting normalized coordinates to value, and the other for mapping normalized coordinates to chart area pixels. Now if we invert the first one, we get a conversion from the plot value to a normalized coordinate. We can chain these two, and we get a conversion from plot value to a point on the canvas. It's worth noting what happens to the x-coordinates here. The normalized to chart area is simple. It converts the x-range of 0, 1 to the pixel range from the left side of the chart area to its right side. The other transform converts the 0, 1 range to a range of indices of the values array. So the normalized value of 0 is mapped to the index 0, and 1 is mapped to the last valid index in the values array. Which may seem weird because we are mapping floating point values and may end up with an index of 1.3 or something. The thing is, we don't ever use the x mapping this way. The x part is only used in the combined value to chart area transform, where we invert this mapping. That is, we map the indices to the normalized range, so that the first index maps to 0 and the last one to 1. And we then map the normalized range to the full chart width, ending up with the values being evenly distributed on the x-axis. Here's how this looks in code. We initialize our value to normalized transform with a normalized to value variable. In the next line we invert it, and now the name matches the function. Next, we take the normalized to chart area transform and we concatenate the value to normalize at the end. What this method does is it multiplies the matrix on the right, just like calling translate or rotate. That means the flow of transformations should be read from the end. First we convert the value to the normalized representation, and then to the chart area. To compute a point position, we use our transform, simply providing the index and value, ending up with a point on the chart. We then connect all the points using the stroke lines method. Charts work correctly. Everything stretches as it should, but there is one problem. The chart does not look very professional because the line labels look totally random. If we compare that with, for example, a Google Sheets chart, the latter looks much better. The values are rounded, making the chart look very clean. When we try different value ranges, we see that the number of segments changes, but stays in the range of 3 to 6. The labels are similar as well. They are multiplies of tens, hundreds, ones, depending on the range, or 20s, 25s or 50s. But that's basically it. We'll use this information to construct our algorithm. First, we need to check the range of our values. The lowest value is -16.32, the highest is 1000. So the full range is just above 1000. So the label step might be somewhere in tens of hundreds. This depends on the magnitude of the range. If we were talking about numbers from 0.5 to 0.7, a label step of 100 won't make any sense, so we have to take this into consideration when calculating it. With a step of 50, we will get a lot of segments. With a step of 200, much less. So we need to adjust the step size to the number of segments we want. It may be tempting to use a simple division for that, but that won't work. We need to first expand our range to make sure the chart starts and ends with a value divisible by the step. This ensures every chart line has a round number label. If we choose 50 as our step, the lowest label should be -50, so that the chart contains -16.32. However, if the step is 200, the lowest label should be -200. This increases our range. If we choose 50, the range changes to 1050. With a step size of 200, the range increases to 1200. Now we can divide this expanded range by the step size to get the number of segments. If that number is inside our acceptable range, for example no more than 6, then we found our correct label step. Let's implement this. We add a method to calculate the number of segments needed and the adjusted minimum and maximum y-axis value. Inside, we declare an array of multipliers for our vertical scale labels, along with the maximum number of segments we want to display. The algorithm will try the multipliers from the array, starting from the smallest, and choose the one that results in segment count no larger than 6. The first thing we need is the order of magnitude of the range. Are we in the thousands, hundreds, millions, etc.? This will be used to multiply the step factor. So for example, with the step multiplier of 2 and the order of magnitude of hundreds, the actual step will be 200, meaning we will draw horizontal lines at each 200 level. And that's what we do in the beginning of the loop. We calculate the actual step size. We then use this number to adjust the range so that the new range contains the original range and the beginning and the end of the new range is divisible by our selected step size. For the lower bound, we use the floor method to be sure the new lower bound is the same or smaller than the original. We adjust the upper bound in a similar fashion, using ceil this time, ensuring we are higher or at the same level as the original upper end of the range. We count the segments, and if we achieve the desired count, we stop the loop and return our results. Remember, we started with a very small multiplier of 0.2. This value would result in a large number of segments. Since the multipliers are sorted in an increasing order in the array, after every iteration we end up with a larger multiplier and smaller number of segments. That's why we only need to check if the segment count is small enough to look good. If the loop terminates without a break, it means we mismatched the multipliers array and minimum segment count. Our max segments was too small and not achievable with our range multipliers array. In this case, the function returns a default count of 10 segments and the original range. Note that this can only occur as a result of a programmer's error. With this particular configuration of multipliers and segment count, this should never happen. The method is ready. We need to plug it in to our drawing code. To do this, we simply need to update the high and low values along with the horizontal value span and the lines count. The magic of affine transformations will do the rest, and our chart will now be able to handle all sorts of input ranges gracefully. Note that in this case we ended up with 6 segments, or 7 lines, and a step size of 200. Although the scale of charts changed, the first value is still -16.32, and you can see it's displayed correctly just below 0. This also works for values with different order of magnitude. Here in the main file we use values that are all fractions, and the algorithm still works perfectly. And this concludes the tutorial. We've come a long way together, from a single rectangle on the canvas, through using linear algebra to move, scale and rotate objects, to a fully functional and useful chart control that's able to handle various edge cases. Hope you liked the tutorial, and I will see you in the next one.